Record. Okay, perfect. So today we are going to talk about, I guess you probably already heard of it, which is about the probability. And we're also going to talk about a very important distribution that is almost the most frequently used distribution, which is the normal distribution. So again, to fit in today's lecture into your knowledge structure. So far, in the previous two lecture, we talked about how to deal with two different variables. And specifically, we're trying to study what's the association or relationship between them. And we, in the lecture 7, we talk about quantitative variables, and in lecture 8 we talk about qualitative variable or categorical variable. And today we are actually jump out a little bit out of this framework, and we're going to look at a very basic foundation part of the whole courses. And as you know, when we study statistics, we usually consider like all our events is subject to some randomness. And one important problem is, how do we categorize, or how do we describe that kind of randomness? Can we use a number to describe that? And that is what we are going to talk about for today. And as again, as a disclaimer, then today in today's lecture, we're going to have some mathematical involved, and just make sure that you will have your calculator prepared, and you can also use your the calculator in your computers to join the calculation for today. So at the beginning of the lecture, I would like to start a polling and or a survey. Have you ever learned this like a probability concepts before, probably in your high school or in any other school? Just curious. Okay, yeah, I guess, yeah, that's kind of what I'm expected. So I guess the majority of you probably already heard of the probability, or even take some serious class about that, probably in high school or other courses. So I guess for those students, probably the first half of today's lecture is more like a review. I guess you guys will be very familiar with what I'm talking about. So you can just quickly fresh up your mind about the idea of the probability. And for those students have never taken the probability before, so I would say, because today's lecture will be quite independent with the other lectures, because today is more like a foundation part, and it's more like a the pillar of the all the other lectures. So I guess if you feel it's really hard to understand, you can just put it there, and after the lecture is over, and you can come to my office, or you can watch the video again to catch up with the ideas. And um, so when it comes to the probability, I guess the first problem is, why do we introduce the probability? So the probability, you can consider it as a measure, or trying to uh, uh, a trying to find a way to describe what's the randomness of the event. So if you talk about the probability, even in statistical fields, you will find out that, even in the statistical field, there could be different view on the probability. Some people would consider the probability in this way, and some people will consider in another way. So even in the statistical field, there's not one way to define the probability. But today's lecture, we are going to consider the probability as the proportion of the time that some kind of event occurs over the long run. And because of this definition, in this case, the probability can also be understood as so-called the relative frequency. So for example, say if you bought a lottery ticket, and then you want to know, okay, what's the probability that I win? So if you looking through our definition, you could consider like, okay, I'm going to buy the ticket over and over again, probably weekly or like or monthly. And after a lot of times or a lot of experience, and finally I just look at, okay, what's the proportion that I win or at least win some money for that lottery ticket. And in that case, I could use that type of information to help me to describe, okay, what's the probability of winning a lottery ticket. And another example would be like, okay, so say if you want to know what is the probability of a certain traffic signals to be read as a certain specific time. So using our experimental way, you could do it like, okay, I'm going to commute the work daily, and I'm going to try to stop at that crossover at the same specific time, and then I'm going to observe what is the color of the signal on that day, and then over and over again, I could get a very good sense that, okay, what's the proportion of the times that I will observe a red color on that signal in the crossover. So as you can see that in this definition, we are kind of based on our experience. So we are kind of trying to observing something over and over again. And this is quite related to what we covered in the previous lecture, where we talk about the risk, right? And remember, when we talk about the risk, we say there's three different angles to look at the risk, and one angle is exactly probability. So that's actually the definition for the risk for that part is closely related to what we're talking about the probability for this lecture. However, based on this definition, there's a very important part of that definition. That is, we need to make sure that we are talking about over the long run. So we need to make sure we will, if we talk about probability based on experience, we need to make sure that we do have a lot of data or a lot of observation to make sure that we are drawing the right conclusion. So here is example. Say we are trying to study like what's the probability for a newborn baby to be boy. So if based on our definition, you will think of, okay, so what I'm going to do is I'm going to stay at the hospital and I'm going to just stay there and observe and keep the record about what's the sex or what's the gender of the new baby on that day. So here is a results that somebody did that before. So as you can see that on the first week, we only have around 42 samples or 42 units. And, oh, sorry, 30 units. And out of the 30 units, only 12 of them were boys. So based on this, our definition, the proportion of the boys should be like a 0.4, right? But can we say that the probability of a newborn baby is a boy is zero point 0.4? Well, that's not fair because we only have 30 babies in our observations. So that's such a small number. Because when we talk about the probability, we need to consider the over the long run. So we have to keep the recording over and over again until we have a relatively large number, say 1,000 units, and that's probably okay. So as you can see, after 42 weeks, which is almost a year, and we get 1,200 babies, and all of this amount, and we have around 618 to be boy. And based on that definition, we will get the proportion will be like a 0.515. So this definition, this results is much more reliable than our uh, original estimation, because our original estimation is only based on very short period, and which is actually not what we defined in the probability. So yeah, just the take-home message is just keep in mind that when we talk about the probability, we're talking about over the long run. That means we need to make sure that the sample size is large enough, and we need to make sure we repeatedly observe the units to get the results. So based on this definition, we actually have two different ways to determine the probability. So the first one is just to make an assumption based on the physical nature of the events we have. For example, say, what's the probability we get a heads after flipping a coin? So in that case, we can just simply assume that, okay, we just assume this coin is fair, and which means the probability we get a heads and the tails is exactly the same. So based on that assumption, then we can just claim that the probability of the heads is just 1/2, right? Because each event has the equal probability. And likewise, for rolling dice, uh, it's the similar case like that. We can just assume that, okay, this dice is really fair, so the probability to get each number is exactly the same. So in that case, the probability of getting 3 will be 1/6 because this dice is fair. We do have that assumption that each phase will have this same likelihood or same probability to be chosen. As you can see in the method one, the characteristics is that in the method one, we didn't do experiments. We just based on our say our assumptions or our prior knowledge about the events we have. And as you can imagine, in the real life example, for a lot of events, we have no idea like what's the nature of that because that's not so simple like the coin or the dice because we it's really hard to make the assumptions that we think that is reasonable. So in that case, we will use methods two to determine the probability, which means we are going to observe in the long run what's the relative frequency that would happen based on the experiment. So again, just like the example that we determine the probability of deliver a male gender of the babies, we can just observe what's the gender for the baby in the long run and to get a sense of the probability in that way. So basically, these are two different ways to determine our probability. So any questions so far? I guess it's quite straightforward, right? So, okay, so after talking about our definition of the probability in this lecture and also how we determine the probability, then I'm just going to probably help you to review certain important rules that we applied in the probability. So based on our definition, as you can see, that probability is something like a relative frequency, right? Which means it's some kind of proportion out of our total events. So based on that definition, so if I ask you to use a number to describe the probability, what kind of characteristic you would imagine our numbers should be like? So exactly, because the probability is getting the ideas getting from the proportion, right? So proportion is something range from 0 to 1. So we kind of just apply the same idea to our probability itself. So we also consider our probability should also range from 0 to 1. So when we're describing our events, so if you consider the event could be scaled from one extreme to the other extreme, and the first extreme is that the event will never happen, and it has zero likelihood to be happen. And another extreme will be these events will always happen. So which means because our value is ranged from 0 to 1, so that's why we considered the probability equals to 0 refers to the case where our events will not happen at all. And we say the probability equals to 1, that means our event will definitely happen, or we will say it will always happen. So notationally, we use the the letter P to describe the to denote the probability. So this P, as you can see, is in short for probability itself. So the second important rules, that is our probability for the complementary events must sum up to 1. So what is the complementary event? You can consider a certain figure like this. So say our event is A, and U is our all of the possible events. So our A prime over here will be all of the events that is not overlapped with our original event A. So so this A prime will refer to our complementary event. So we will, in mathematically, we will say these two events are complementary with each other because it is kind of either A or A prime things. And the most important thing is that because as you can imagine, these two events will make up our total event, which is U, which is the complete possible event. So which means you can imagine because that's all events we have. So this event will definitely happen for events in U, right? So that's why the probability we get from A or probability the event A prime happens should sum up to 1. So that's the idea for the complementary event. So one possible example for the complementary event could be like the flipping a coin. So because when you flip a coin, it's either heads or tails. So you cannot have the other choices, right? So in that case, we would consider that two outcomes are complementary with each other. So in that case, it should also follows this type of the rules. So okay, let's try to do an exercise. Say like we have like the heads for 400 times out of 1,000 times. So what is the probability of landing on tails for these coins? Just based on the rules over here. Yeah, I guess all of you get it right. So the answer is A, because if you, based on our definition of the probability is a proportion of an event happening. So based on that, the proportion will be 400 over 1,000. And in that case, the probability of our event, which is the heads of our coin, will be 0.4. And A prime will be the complementary of that event, which is the another event other than heads. In our case, it will be tails, which is what we are trying to looking for. So in that case, we would expect the probability we get from A prime will be 1 minus the probability we get from A. So in that case, it will be the answer will be A, which is 0.6. So just remember, as there are some students still not quite getting what is the meaning of A prime. So the A prime is, you can just consider like it's the event other than the event of the A. So in our case, for example, for the coin case, our event is the heads, then the A prime will be the opposite one, which is the tail. And say if we roll a dice, if our event is getting 3, and the A prime in that case will be all the other numbers that other than 3. So it's kind of like the opposite thing. And similar to the idea of the complementary events, because complementary events is kind of just talking about either A or A prime. We probably can generalize this a little bit. So we just don't consider like just two events. So say we have more than one event, but we only care 2 out of them. And in that case, we will more focus on the idea of the mutually exclusive. So the mutually exclusive, it's very similar to the complementary event, but complementary event is a more special case of the mutually exclusive case. So here, the mutually exclusive is just referring to that one or the other occurring. And in our graph, you could consider like we have a lot of events in our event set, but we only look at 2 out of them. And but for these 2 events, it's just like either A uh, or B. So A and B will not happen at the same time. So in this case, we probably have more than one event, but we just look at this too. And we would not say A and B is complementary because B is not just not A, because we still have the other event can also define as not A, right? So that's the small difference for our mutually exclusives to the complementary event. So for the probability rules, so if we say 2 events are mutually exclusive, then we need to make sure that uh, if we say the one thing happened from A or B, it will be equals to the sum of the probability of either of them happen. So that's all of the property of the mutually exclusive. So you can imagine that, say, you taking a dot out of this graph. So this dot cannot be A and B simultaneously, right? So you can imagine that the probability of taking the dot, it will be the same as the proportion of this region out of this rectangular plus the region of the second one out of the rectangular. And because these 2 events are mutually exclusive, so the probability of A and B happened is 0 because they cannot happen at the same time. So that's based on our definition. So one possible example would be like when you're driving the cars. So there are 2 events. You can turn left or you can turn right, but of course we could have other events. You can go straight, you can go ahead. But right now we're just looking at the turning left and turning right. But for these 2 events, we consider it's to be mutually exclusive because you cannot do the same thing at the same time, right? So in that case, this will follows the rules of our mutually exclusive here. So the probability of you turn, which is the probability either you turn left and turn right, uh, will be equals to the probability you turn left plus the probability you turn right. So that's the idea for the mutually exclusive. So um, I guess the one possible way for students to get confused for this part is just they just kind of fail to tell the difference of this mutually exclusive with our previous complementary events. Because the complementary exam, I'm just trying to answer the question from the chat, that it's just about an event happen and the event not happen. So it's kind of like just either the event or the another one. So these 2 pieces will form the complete the complete event set. So that's the difference from our mutually exclusive. Okay, so let's try another iClicker question. So say we have 2 dices, and we present what is the probability of we getting the sum of the 2 dice together, and we show what's the probability of that in this uh, in the above the bar. And the question is, based on our mutually rule, what's the probability that we're ruling a sum that is greater than 11 when we're rolling 2 dice? When we're rolling 2 dice. So for this question, what we know is that we have 11 different events, right? So because the event over here is the sum of the two numbers of our of each dice, right? So the smallest one could be 1 plus 1, which is 2, and the largest one will be 12, which is out of the 6 plus 6, right? So right now we could have 11 different events, and for each event, their probability is writing over here. And right now, what we are trying to do is to look at the event of rolling the sum, which is greater than 11. So which means we are looking at these two events. Because when the sum is greater than 11, so first of all, it could be exactly 11, or the event could be, our result could be 12. So we are looking at these two events. So in our case, the event A will be 11 over here, and event B will be our 12 over here. Because for now, like all of, because when you roll a dice, say you get a number out of these two dice, this number, that is it, right? So you cannot get another number simultaneously. So that's why we consider each event to be mutually exclusive, right? So based on that rules, if you consider our event 11 to be event A and event 12 to be event B, then how do we compute what's the probability we have greater than 11? I guess you probably need a calculator to do that, because yeah, it's a very small digits over here. Okay, I'll give you 20 seconds to consider this question. Oh wait, I only have I only have A and B and C and D. That's my bad. I need to change this. Wait, sorry. I believe I can change the question type. And sorry about that. Okay, yeah, here you go. So yeah, I see the student did it correct. Yeah, my bad. So for this question, because you can consider 11, 11, and the event 11 and event 12 to be exclusive with each other, and because it's either one happened, but not both. So the event, what we're interested in is the events that the number is greater than 11, and that's only out of the two possible way. One is we rolling 11, another way is we rolling 12. And in that case, because of the mutually exclusive, we can just write that as the summation of the probability for each separately. So that's why we would get our results to be just to look up the probability for each event and take the sum of it. Okay, yeah, I'm sorry about the iClicker. I thought it was the multiple choice. Okay. So any questions so far for this example? I think it's straightforward, right? Okay, so now let's look at another rule that is actually very important. So this rule is also talk about two events, but the different thing is that we say two events are independent if we talking about that one event has nothing to do with another event. So it's not like our rolling dice example, because when we get the events of the 11, it do has something to do with the events of 12, because if you roll 11, you cannot get 12. So this 2 is not independent. So it's not quite like that one. So the 2 events is more over here is more like a 2 events of the 2 different measurements. For example, if I measure your, say, your height, and I also measure your weight, and then what's the relationship of these 2 events? It's more like the discussion over here. So when we say independent, we mean that one event does not influence the probability of the another. And if we are sure that 2 events are independent, then mathematically, we can write the probability of A and B happened will be equals to the product of the probability of each event separately. For example, say the probability of we sample a random student from the class, and that student is male and it's from the course code 1023. So this probability will be exactly, I randomly draw a student who is a male times the probability I randomly draw a student who is from the class 1023. So that's the idea for the independence. So trying to distinguish the 2 events over here with the 2 events in a mutually exclusive example. So again, I just adapt a little bit for the example over here. So right now, we are not just rolling 2 dice, we also are flipping a coin. So now tell me, what's the probability that we rolled the sum of the dice to be greater than 11 and we flipped the coin which say heads? So right now, I think you will need the results in the previous question, so I just present it here. So which means additionally, we just kind of introduce another event, which is the flipping coin. But of course, I didn't mention it in this question, but we just considered the coin flipping and the dice rolling should be independent. Okay, so I guess so. Right now, you can kind of see that. So these 2 events is not like the 2 events in our previous question, right? So the previous question 2 event is like 11 and 12. So it's more like the same event because we just rolling the dice but have the different outcome. So that's what we're talking about 2 events in the previous question. But right now for this 2 events, it's more like a really 2 events. One event is flipping a coin, and another event is rolling dice. So right now, because of the independence, so which means what we care is that what's the probability that we get x is greater than 11, and we get the heads in the coin. And because these 2 events are independent with each other, so we can just write it out as the product of the 2 events separately, right? And then because the first probability is just out of our previous question, and also the probability we're getting heads is 0.5. So in that case, we just, the probability of we get the sum greater than 11 and the flipping the heads will be given by our original probability times 0.5, which is 0.417. So yeah, I'm just trying to use this example to show you when we talk about the independent, the 2 events is not so similar like the 2 events we're talking about in the mutually exclusive. So another idea, which is kind of apart from the mutually exclusive, is like one event is completely contained in another event. So if you look at this diagram, we would say the event A is completely contained in our event B. So just use our rolling dice example. Say our event A is with rolling 11, okay, and our event B could be rolling the sum of the two dice, which is greater than 11, because for B we have two outcomes, either 11 or 12, and for A it's just 11. So in that case, our event A is completely contained in the event B. So if we have such kind of relationship of the two events, then we can say mathematically the probability of we getting the event A is smaller than the probability of getting B. So intuitively, you can think about this graph. Like the area of A is actually smaller than area B, and uh, also the number of the events in A is smaller than the number of the events in B, right? So definitely B is much more likely to happen, because if A happen, B will definitely happen. So that's sort of the information out of this diagram. So let's try this example. So right now we have two events. Say one event is the world ends due to the global warming, and another event is the world ends due to the global warming in 100 years. So which probability is greater? Okay, yeah, the majority of the students choose A. So let's try to fit the events in our diagram. So if you consider the world ends due to the global warming, I think it fits better to B because it's a more general case. And the world ends due to the global warming in 100 years is a more specific case because, the world ends due to the global warming in 20 years. If this event happened, then the previous event is automatically happen, right? Because the previous event is just about the global warming. So it's just about B. So the answer is A. So I got a question from the chat that there's a student that is unclear about the complementary versus the mutually exclusive. So in terms of the example of the heads and tails, uh, why not it is a mutually exclusive? So for heads and tails, that is mutually exclusive. So in fact, the complementary event is a special case of the mutually exclusive. So if we say A and B is complementary with each other, then we will say they themselves will be mutually exclusive. But it is not the other way around. So if A and B is mutually exclusive, they might not be complementary because there could be some other event could be happen. Okay. So 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 far we have discussed the different probability rules that involved when we're defining the probability. And also just getting the idea from our conditional distribution that we taught in the previous lecture. And we can likewise to define the conditional probability. So remember, the conditional distribution is defined as the distribution of certain variable holding another variable to be fixed, right? So that's the distribution considering two variables simultaneously. And likewise, for this case, the conditional probability is also defined as the probability of one event happen, holding the results of the another event to be fixed. And the idea for this case is very similar to what we did when we talk the risks or talk the proportion in the risk in those examples. So for example, we can say the conditional probability of when the weather is sunny, the probability of the cat to be happy will will be given certain thing. So the calculation over here, you can imagine, is exactly the same as we calculate the risk, or as we calculate the percentage. So it's just that notationally, we will write this as the P because it's a probability. And we use a bar in the middle to distinguish our event apart from our condition. So the something after the bar will be our condition, and something before the bar will be the event that we are talking about. So for this notation, we're talking about condition on the sunny weather. So in that case, we will look at the conditional distribution of the sunny, which is the first row, right? And then we look at the events of happy mood. And in that case, out of this conditional distribution, we're looking at this event. So we will compute the conditional probability as the 10 out of 10 plus 2. So as we can see, this is exactly the same as the as we calculate the risk, right? And also for the conditional probability of raining given sad. So because the condition is sad mood, so it's a mood. So we talk about columns, right? So the condition is actually looking at the second column. And event is raining, which is this event. So the conditional probability will be 4 out of 4 plus 2. So still, this is exactly the same as we calculate the risk. But here, um, just keep in mind that if we just calculate the probability in this way, there is a concern that, as you can imagine, all of the numbers in these tables is really small. Like some of them is just one digit, right? And as you remember, when we define the probability, we say probability is something in the long run, which means we think the probability as something um, in a large sample size. So in that case, we need to be really careful about the interpretation here, because the probability represent in this place is not so accurate, because it is out of a very small sample size. So if we say we have 1,200, and we pretty much could say this results could be more accurate. Okay, any questions so far? Okay, so if there's no questions, so we conclude the first part of the lecture, and we will have 10 minutes break, and we will be back at 2:25. And after the break, we will talk about the normal distribution. Hello, everyone. Let's go continue. So in the second half of the lecture, we're going to talk about the normal distribution. So again, before we talk about this part, I would like to do a survey. Have you ever heard of normal distribution before? So A is yes, B is no. Just a quick survey. Okay, I kind of have half, and now it's 2 to 1. Okay, uh, I guess the normal distribution it's very frequently used in almost every scenario. I couldn't think up with one field that there's no normal distribution because it's so common, and that's actually one reason that we call it normal distribution, because that's just the things that we think is normal. So to talk about normal curves, I think we need to start with, or to fresh up our minds with the idea we already learned in probably lecture 3. So in lecture 3, we talk about uh, how we plot the histogram, and we know that there are two different types of the histogram based on our scale of our y-axis. So say if our y-axis is just the count or frequency, then we would say that's our original type of the histogram, right? And also sometimes we would like to transform the y-axis by scale it by divided by the total number of the counts. And in that case, we would by that time, we call it the relative frequency, if you remember. So the good thing that we transform from the counts to the relative frequency is that right now we change the representation of each bar in the distribution. So in our original histogram, the bar represents the counts. We will tell how many people or how many units in a certain range. So that's the information we tell from the original histogram. But after do the scaling, our interpretation changed. So according to the y-axis, it's not telling what's the count, but instead it's telling us about what's the proportion. Okay, I'll move this a little bit. So in that case, each region, you can consider the region of this one. It will tell us uh, what's the proportion of the units that located within the range of our x-axis. So basically that only change a little bit about the interpretation, but for the shape, it does not change at all. And right now, we were going to introduce an even more special type of the histogram, which is the density the histogram. So for the density histogram, the special thing is that so the area of the bars will sum up to 1. So by area, actually, I think a more fair way to say is the sum of the y value for each bar should be 1. So if you measure the y-axis for the first bar and measure the y-axis for the second bar, and so on and so forth, and you add them up, that sum will be 1. So for the density histogram, the proportion will be exactly what's the proportion uh, of our of our uh, uh, I would say the proportion out of our population, and that is located within certain range. So this is because that if in fact, if we just scale our counts according to the total number of the count, we will automatically get the density. And in the previous lecture, uh, we already considered the scaling in that way. But like for the relative frequency, that one, sometimes we could scale it by the other number. But the total number of the counts is the most uh, is the most or the best choices among the most of the time. So after describing the density histogram, then we are kind of making it to a more special case. Okay, so I'm answering the question in the chat first. So um, is the relative frequency histogram the same as the density histogram? So in fact, the relative frequency, that one is we will consider the density as a special case for the relative frequency, because the relative frequency is just scaled by something. It does not have to be the total count, but the density is just scaled by the total number of the count. So for the relative frequency, it's actually a more um, it's a more general case. But in fact, in a lot of scenario, when we talk about relative frequency, we usually scale it by count. So in that case, it is actually the same thing. But just keep in mind that we do can scale by the other number, but scaled by the total number is the most frequent choice. So that's why in practice, we usually just consider the relative frequency the same as density, because we sometimes we just think by default we scale by the total number of the counts. But just we have to admit that for the relative frequency, if we scale by the other number, that's not wrong. But we usually just scale it by the total number of the counts. But for density, it means we definitely scaled by the total number of the counts. So that's the difference for these two concepts. Okay, so after introducing the density histogram, then we go into a little bit extreme. So far, I guess in the lecture probably 3 or 2, we discussed that we could change the beam width to kind of change the characteristic of the plot. But now just imagine that in the previous case, if we change the beam width to make it more narrow, and because we are short of the data, right? We don't have that many data. So at that time, if we decrease the beam width, we will expect a lot of empty bar in the middle. So that's at that time we regard that's a really bad thing. But for now, just consider that we able to adding the data unlimitedly. So which means we no longer worried about the after decreasing the beam width, there could be a missing in between those beams. So if you just decrease the beam width, and as you can imagine, the plot of the distribution will be more and more smooth. And finally, into some extreme, we could use a line or a curve to describe the shape of this density. So in this type of the curve, we will call it the density curve. And likewise, for the second distribution, and if we just keep decreasing the beam width, and finally, we will get a curve, and which is very, very smooth. So similar to the idea from the previous, the density histogram, that the y value should be sum ups to 1. And this should also has the same property. You can imagine this curve is out of infinitely many of the small bins. You can consider each dot is out of this very, very narrow bin, which is almost a line. You can imagine something like that. So in that case, if we sum up all of their corresponding value, it will be the same thing to do the integral. So I'm not sure whether you learned the integral yet, but if you don't know what is integral is, then that's fine. You can just consider that for this case, the area under the curve should be exactly equal to 1. So that's the message for the density curve. So which means this region, that the region that's under the curve should be exactly 1. And likewise to this one, the region under the curve should be exactly 1. So that's the property for a general density curve. Any questions so far for the density, about how the density curves comes out? Okay, if no other question, so now I'm going to officially introduce the normal density curves. So the normal distribution is also called the Gaussian distribution, and which is trying to use to memorize the very famous mathematician, the Gauss. And because of that, the normal density curve is also known as the Gaussian curve. And so that's the Gaussian curve is more frequently used in mathematical fields as well as the statistical fields. But in the real life, we prefer the normal word. So why do we why this distribution is so common and is so popular in both the research in our real life? So first of all, the normal density curves, as you can see, it has a lot of nice property. So first of all, it has a bell shape. And later on, I'll tell you why bell shape is good. And also it is unimodal, which means it does not have a very complex structure. So for mathematician and for statistician, they like simple things. So unimodal, which means we can kind of avoid some complex structure. And another good property is that it is also symmetric. Uh, and symmetric can also is a very nice property in mathematics. And if you look at the examples, then you will know why we call it normal distribution. So this distribution can be used to categorize or can be used to describe a lot of um, different distribution of the data in real life. For example, we can use it to describe what's the distribution of the height in the general population, and we can use it to describe the weight, the sleeping time, IQ index, or even BMI. So why it's called normal? So first of all, you can see that all of this index or measurement, they kind of have some kind of the normal range, right? So we would expect the majority of the population should be within the normal range. And if we the far away from the normal range, the fewer people we would expect in this measurement. So that's exactly the same as our bell shape. So the bell shape means that we have our highest point located at our middle or at our mean. And the far away our value is away from the mean, the, the, small, the smaller the probability we would expect. So uh, that's why we would frequently use this shape to describe our real life data, because in many real life data, that is pretty much our our pattern over here. And of course, we have some simplicity in a normal distribution in a sense that we consider the symmetry. So which means, say our average height is, I don't know, say like a 170 centimeters. And then if you plus 10 centimeters or minus 10 centimeters, it will has exactly the same probability. So that is the message from the symmetric. And another good property for normal distribution is that as long as we know what is the mean and our standard deviation of our population, then we could just use these two information to categorize to characteristic that our normal distribution. So our mean is actually reflected as our middle point because mean is describing our center, right? And because of the symmetry property, our mean should be exactly same as the median in our case. And also here it is a unimodal distribution. And so our mode is also located at the same place as our median and also at the same place at the mean. So as we can see, this is a really nice property for a distribution. And since right now you know that our mean is reflected by our center, which is also our median and mode. And if you increase the mean of our normal distribution, it will be like shifting our normal distribution to the right. And on the other hand, if you decrease the mu value, it will be like you move our normal curve to the left-hand side. And similarly, for the standard deviation, because the standard deviation is talking about the spread, the spread characteristics. So if you increase the value of the standard deviation, then we would expect our normal distribution will be more spread out because like each data point are more likely to far away from our mean. So that's why our data point will be even scattered more. So that's what we learned from the standard deviation. And just remember, for normal distribution, as long as you know the mean and the standard deviation, or if you take the score, which is the variance, as long as you know these two things, you can exactly draw the normal curve. So that's a really nice. So any questions so far regarding the normal distribution? If no, we will see an example of using the normal distribution. So now I guess we already very familiar with the example of the walking Cheeto. And my friend is a really nice girl. She sometimes also helps to accommodate the other cats. And there's one day, there's another cat called Sushi. Is also accommodated in her apartment. And because she is really enjoying walking the cat outside, and apparently she also wants to take the Sushi into the walking club. And so one day, she trying to encourage the cats to walking outside. So she set up the rule that the cat who walks a longer distance will get the treat. And one day, Cheeto walks like 2.1 kilometers, and the newcomer Sushi walks just zero point 0.6 kilometers. So if you just look at the absolute value of this walking distance, you will say, okay, Cheeto should get the treats. But some people might say, wait, Cheeto is Cheeto is very experienced walker. He has a lot of chance to walk outside, so it's not hard for him to walk like a 2.1 kilometers. But Sushi is like a beginner, and she didn't really have much experience of walking outside, so probably 0.6 kilometer is already challenging for her. So then, if we just compare the digits, it possibly not fair. So in order to make it the comparison more fair, we would like to consider what's the distribution behind the walking distance. So the walking distance can also be regarded as the normal distribution because like for the majority of times we just assuming that the level of the walking distance should be around sometimes, and it's really hard for the cast to be working especially longer or um, especially shorter. But of course, that's just the assumption. So we assume that our working distance is following this normal distribution. And as you can see that the on average, the Cheeto will walk a much longer distance than sushi. And also, you can see that the performance of the walking distance for Cheeto is also not like stable as sushi because the distribution is spread out than the distribution of the walking distance of sushi. And in terms of the numbers, you can see that the standard deviation is also larger than the standard deviation of the sushi. And so the so since what we are trying to do is to compare like what's the performance of the 2.1 just in the general distribution of the Cheetos uh, in Cheetos distribution comparing to zero point 0.6 in the general population of sushi's distribution. So some people might say, okay, I just compare their walking distance to their mean. So if you do that comparison, so which means you will minus 2.1 to the mean, which is 2. And in that case, you will get the difference to be 1 kilometers, sorry, 0.1 kilometers. So which means on that day, Cheeto has extra zero point 0.1 performance than average. And for sushi, if you do the same calculation, zero point 0.6 minus zero point 0.5, you also get 0.1. So which means sushi also on that day, her performance is also 0.1 kilometers better than the average. But is these two difference the same thing? Because if you look at the distribution, um, the distribution for the Cheeto is much more spread out, and the distribution for the sushi, however, is quite clustered. And so, which means it's quite easy for Cheetos to do a much better job. But for the sushi, because her performance is kind of clustered around the mean. So it's really hard or it's really rare for hers to get a very um, extraordinary results. So if you consider the standard deviation, actually this 0.1 difference is better than the 0.1 difference in the distribution of the Cheeto. So this is what we are trying to do in the comparison after considering the normal distribution. So to fairly compare two different values with their distribution considered, we will introduce a so-called the standardized scores. So which means we are going to minus our value by the mean of the distribution and divided by the standard deviation of our distribution. And that's how we calculate our Z-score. And in that case, we will just directly compare what's the Z-score in their results. But here, this comparison relies on a very important precondition that we assume that our distribution follows a normal distribution. So which means in our example, if our distribution is not normal, then we cannot use this way to do this to help us to do the comparison. So that's very important. This is the precondition for what we are doing in this example. So in Cheeto's example, if we calculate the Z-score, we will start from the value on that day and minus the mean and divided by the standard deviation. And after calculation, you will get something like 0.2. So what's the interpretation for this 0.2? The interpretation for this 0.2 is like on that day, the Cheeto's performance is 0.2 times standard deviation above the mean. So basically, this z-score is telling us like how much times the difference is in terms of the standard error. So that's the message from this z value. And now let's do an exercise. So now tell me, what is the z-score for sushi? Just based on the distribution for sushi. So right now we know that on that day, she walked 0.6 kilometers and the mean is 0.5, standard deviation is 0.1. So what is the z-score for sushi? Okay, so yeah, I guess majority student get it correct. So the answer is 1 because it's 0.6 minus 0.5 divided by the standard deviation. And for the calculation for the z-score, I would like to emphasize that the denominator is the standard deviation, not the variance. So say if in the question I give you the distribution of the normal using the variance, then you first need to transform the variance into standard deviation before calculating the z-score. So just pay attention to that. So similarly, after getting the z value for the sushi, we can interpret that for that day, sushi's performance is actually 1 times standard error better than the average. So as you can see that if you just, in terms of the distribution, actually sushi is did much better than the Cheeto because Cheeto is, I mean, uh, in absolute value, Cheeto works longer distance, but comparing to his ordinary performance, that day is not special. But for sushi, you can see that it's 1 times the standard error better than the average. So you can see that for today's performance of the sushi, it's much more special than the performance of the Cheeto. So in that case, it seems sushi is more deserved the treats. So that example is pretty much the idea of introducing the normal distribution and use that information to help us to do the comparison. And in fact, we can just to use this property of the normal distributions to build the empirical rule. So because for normal distribution, once we know the mean and the standard deviation, we can already draw the curve of the normal distribution. And also, a very nice property is that if you look at what's the percentage of the data that located within the range of 1 time standard error, which means from the range of mu minus 1 standard error to the value of mu plus 1 plus 1 times standard error. So this region will have around 68% of the data. And this result is true no matter what is our standard deviation or our mean is. So this is true for every normal distribution. And also, if we look at wider in terms of the standard error, if we look at the range from mu minus 2 times standard error to the mu plus 2 times standard error, this region will be around 95%. So which is a really large percentage. So as you can imagine, so after knowing the standard error and knowing the mean, we can roughly tell like what's the majority of the range of the people. So just based on this range, it will include like 95% of the people located within this range. So we can use this information to help us to create the range to include a certain percentage of the data. And if you look at even further for this three times the standard error, the range will be really, really large, which is 99.7%, which is almost includes all of the data. So the shape of the normal distribution is like that. So as you the far away you from the mean or the median or the mode, the more closer you will be to our x-axis. But this curve will never touch the x-axis. So it will trying to close as much as possible, but never really reach the x-axis. So we will always observe, it's always possible to observe extraordinary large or small data out of our certain range. But as you can imagine, the probability is really, really, really small if we consider a large or a wide range of it. And also, we can use this information to divide our normal distribution into different regions. So we could say on this region, which is the place that my mouse is moving around, this region will makes up 34% of the data. And this region is 13.5, and this is 2.35, and so on and so forth. So just the take-home message is that just remember, this result is for general normal distribution. So it is true for any mean and standard error, as long as you know these two information. Okay, so let's try to use that information to do an exercise. So right now we are interested in what's the distribution of students' height. And we assume that they are normally distributed. And we have mean of 165, and the standard deviation is around 10. So just based on our empirical rule, can you guess like what's the proportion of the students which has a height between 145 to 185? So you might need this graph to help you to do that. So first of all, you need to calculate what's the z value for each for for uh, for each value over here. Okay, so let's calculate the z value one by one. So first of all, for 145, which is our lower bound, if you compute the z value, which is our value minus 165 divided by 10, which is -2. So there should be a negative sign over here. And that will represent this region, because that's about the region of the 2 times the standard deviation. And if you look at the upper bound, which is 185, and you will also get a 2 times standard error. So which means it is something about, sorry, it's something about this region. So which means when we consider the range of 145 to 185, we're actually looking at this range. So it will make up around 95% of our data. So I guess now you pretty much get the idea of what we're doing right now, right? So then trying to work on the second problem. So say what's the proportion of the students had height between 145 to 175. So for this example, we just changed our upper bound and our lower bound is exactly the same. So remember, for this question, just trying to compute what's the z-score for each value, because we want to know like how far in terms of the standard deviation is that value to our mean. Okay, I guess the majority student get it correct. So again, if you look at the lower bound, uh, which is still the same, so which means in the first place, we are looking at this region. And however, for the upper bound, if we compute the z-score, it will be 1. So which means instead of the complete region, we'll just look at the first region because that is because our upper bound is 1 standard deviation away from our mean. So from this region, you just sums up uh, the percentage of each region. You will get the percentage will be the B. Okay, any questions so far for these two examples? Okay, so there's an example. I think it's about. Oh, there's a question. I think it's about the curve of the normal distribution. So for the normal curve, um, what I said is that I mean when the curve is far away from the mean, it will be very close to 0, but it will never reach 0. It will never be exactly 0. So as you can imagine, this curve can reach the positive infinity to negative infinity. But even if it's really, really large, I mean, the x value is really, really large, the value on the curve will very close to 0, but it will never reach 0. Okay, any other question? So there's a very small chance to have an infinitely tall person. Yes. So if we consider the distribution of the um, uh, if we consider the distribution of the height as the normal distribution, that is true. But of course, that's a very strong assumption because like the height couldn't be negative, right? It couldn't be 0. So for that case, we usually just use the normal distribution to approximate the height because for as you can see that approximation is very reasonable because uh, like a lot of people is within certain range, and you can see that when the value which is really far away from the mean, which is really not like is not probable. So in that case, we could fairly use the normal distribution to approximate those data. So that's the idea of the normal distribution. Okay, so there's a question about how I get 81.5. So this question is about asking the percentage of the percentage of the certain value, right? So right now we are implementing this empirical rule. So what we are doing is basically we look at the bound for this range, and we just look at how far in terms of the standard error for this value from our mean. So which means first of all we calculate the z-score. So for the lower bounds, we calculate the z-score, we get -2. So which means our lower bound is somewhere located here, right? In our original empirical rule map. And for the upper bound, based on the z value, it should be 175 minus this divided by standard error, which is 1. So which means our upper bound is in fact located at this place. And then uh, because we are looking at the data within this range, right? From our lower bound to upper bound. So basically we just summed up all of the percentage for each region, right? So in our case, the region of this will be 13.5% plus the double of the 34%, which sums up to 81.5%. Okay, so there's a question about what makes complementary events special, mutually exclusive events. So the complementary events is just talk about two events, right? We just talk about either A or not A. So we only have these two events. But for mutually exclusive, we could have A and we have B and we have not A and not B, right? So we could have some like a we could have A, B, and others. So we could have like a we could have some other events other than A and B. So that's the difference for the complementary and the mutually exclusive. So this pretty much concludes the lecture today. And for this lecture, we will have a reading material prepared for you to understand why sometimes our intuition could be different from the relative frequency that we computed, and which is very interesting topic, I think. And I also prepared the post-reading quiz, and still we have two questions this time, and for you to check whether you understand the material or not. And just a kindly reminder that we have uh, assignment 3 due on November 23rd. Um, and so I will accept the assignment till November 26th, but the official deadline is November 23rd. And our midterm 3 will be located, will be on the November 26th. And again, this time the proctoring will be the same as we did in midterm 1 and midterm 2. But the difference is that for this time, we could have some fill in the blank question, because as you can imagine, we could have some calculation in uh, the previous lecture and in this lecture. So the calculation could about like what's the odds ratio, what's the relatively risk, and what's the odds and what's the risk and something like that. And for this lecture, you might ask to compute the z-score or compute the range, which is pretty much like the practice question that I will upload it probably today or tomorrow. So any questions so far for the midterm? So if there's no other question, so that is pretty much for today. And I'll see you guys for the next week.
I actually have one quick question.
Yeah.
So for the midterm, you said that there's fill in the blank.
Yeah.
And is that because we get part marks if we show like some of our work, but then we like mess up somewhere? Or is it because it could technically just be a multiple choice if our work doesn't matter, you know what I mean? But like
Yeah, it's because I mean for the fill in the blank question, because I won't ask you to show your like a show your step. So it's just like asking the results. But it's so for the computation, not all of the question will be in the fill in the blank. Some of them will be in the multiple choices, and some of them will be just fill in the blank.
Okay, I was just wondering because sometimes like you could be doing it right and then mess up somewhere. So I thought maybe that would be too difficult to mark, but I just like I was wondering
Oh
what.
yeah, yeah, yeah. So because I won't require you to show your set, so you can guess a value and still get the right. Yeah,
Okay, thank you so much.
you're welcome.
I also just had a question about assignment number 3.
Yeah.
So I'm choosing to do the debate data set, and I was
Mhm.
just wondering because the first part is asking us to compare the two quantitative variables,
Yeah,
and I
yeah.
was wondering if you want them as two separate like colors of data on the same graph, or you want us to put it Trump versus Biden votes.
Uh, you mean because I don't think you can put it in two colors, can you? Because you.
You can do it as two different data sets on, and like the y-axis can just be the states, or the x-axis, my bad, can be the states, and then we can have the different colors for the votes. I just wasn't sure what you wanted the
Oh
two
no, no, no,
variables to be for
no.
x-axis and y-axis.
So yeah, yeah, yeah. Good question. So for that assignment, I so for that question, you just consider the case in general. Don't separate it according to the states or other variable. Just plot the vote for Biden versus the vote for Trump.
Okay.
So there is no
Okay.
like a stratification or
Perfect.
yeah,
Okay.
just
Thank
treat
you.
all of data together. Yeah.
Yeah, I was just confused about that. Thank you.
Okay. No worries. Okay, so if no other question, I'll see you guys next week. Bye, everyone.